Hello there, and welcome to the Sleepster, your cozy corner of curiosity, where science comes with a side of serenity. Whether you're winding down after a long day, tucked under blankets with your phone propped against a pillow, or simply letting your mind float gently toward sleep, I'm so glad you're here. Tonight, we're setting our sights on a truly captivating idea, one that has fueled dreams and sparked countless stories. Can we bend time with technology, from ancient myths of controlling destiny to the sleek, impossible machines of science fiction? The thought of manipulating the very flow of moments has always held a powerful grip on our imagination. Imagine stepping back to a cherished memory or leaping forward to glimpse what's to come. It's a concept that seems utterly fantastical, defying every tick of the clock we know. But what if I told you that, in a profound and scientifically verifiable way, time is already bending all around us? What if our technology, quietly and precisely, already accounts for this cosmic flexibility every single day? Tonight, we'll gently drift through the real science of time, exploring how speed and gravity subtly stretch and compress the fabric of moments. We'll uncover how our everyday gadgets rely on these very principles to function. And then, with a quiet wonder, we'll peek into the more speculative realms of physics, where the universe's most extreme phenomena hint at possibilities that still feel like magic. Don't worry, the goal isn't to keep you wide-eyed with paradoxes, but to let your mind float gently with the astonishing realities of our universe. After all, the science of time is a story of incredible elegance, a delicate balance of forces that governs everything from the hum of a particle accelerator to the precise beat of a satellite's clock. So, let's settle in, take a breath, and begin our gentle journey into the fascinating question: can we bend time with technology? The idea of manipulating time has captivated humanity for centuries, a staple of myths, legends, and countless works of science fiction. From H.G. Wells's iconic Time Machine to the intricate temporal paradoxes of modern cinema, the dream of stepping outside the relentless forward march of moments has always sparked our imagination. But beyond the fantastical narratives, what does actual science, especially modern physics, have to say about the possibility of bending time with technology? Is it a mere flight of fancy, or does the universe itself hold secrets that hint at such capabilities? Our conventional understanding of time is that it's a universal, unchangeable constant, ticking away uniformly for everyone and everything. This intuitive perception makes the notion of bending time seem impossible, a violation of the very fabric of our reality. However, this classical view of time, as a fixed backdrop against which events unfold, began to crumble at the dawn of the 20th century with the revolutionary insights of a single brilliant mind, Albert Einstein. His theories redefined time not as an independent entity, but as an integral dimension interwoven with space, forming a flexible, dynamic structure called space-time. And within this redefined reality, bending time, in a very specific and scientifically verifiable sense, becomes not only possible, but an observable phenomenon. So, while we might not be building devices that let us revisit last Tuesday or skip ahead to next year's holidays, the universe itself, through the elegant mechanics of relativity, already demonstrates that time is far more pliable than we once believed. The real question then shifts from if time can be bent to how it bends, and whether our technology can ever harness these natural principles to achieve effects that, while perhaps less dramatic than fiction, are no less astonishing. This exploration will take us from the subtle, everyday effects of time dilation to the mind-bending possibilities near black holes, and delve into the colossal energy requirements that currently tether our technological ambitions to the present. The journey into understanding time's malleability begins not in a distant future, but with experiments and observations conducted over the past century, confirming that time is indeed a relative concept. These discoveries lay the groundwork for a grounded, scientific understanding of time bending, revealing that while the grand sci-fi visions might remain out of reach, the universe is already playing its own subtle tricks with the clock. Exploration will touch upon several key areas. First, the established science of time dilation, explaining how speed and gravity already influence the passage of time. Then we'll venture into more theoretical realms, discussing concepts like wormholes and the extreme conditions required for significant temporal distortions. Finally, we'll examine the monumental technological hurdles that stand between our current capabilities and any truly impactful time manipulation, grounding our dreams in the realities of physics and engineering. It's a story not of magic, but of the profound elegance of the cosmos and our ever-growing understanding of its deepest mysteries. Our journey into the bending of time truly begins with the fundamental concept of time dilation. This isn't science fiction, but a core prediction of Albert Einstein's theories of relativity. And it's been confirmed by countless experiments. Time dilation tells us that time isn't a universal, unyielding rhythm for everyone. Instead, its pace can change, slowing down or speeding up, depending on two crucial factors: how fast you're moving and how strong the gravitational field around you is. It's a subtle effect in our everyday lives, but one that becomes undeniably apparent under extreme conditions. First, let's talk about speed. Einstein's special theory of relativity, published in 1905, fundamentally altered our understanding of space and time. It posits that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. These seemingly simple postulates lead to profound consequences, one of the most counterintuitive being that time itself is relative. Imagine two identical clocks. If one remains stationary and the other travels at a very high speed, the moving clock will tick more slowly than the stationary one. This isn't a trick of perception or a malfunction of the clock. It's a real physical effect. We see this in action. With incredibly precise instruments, for example, particles called muons, which are unstable and decay very quickly, are created in the Earth's upper atmosphere by cosmic rays. When they reach us, traveling at speeds close to that of light, they live longer than identical muons created and observed in a laboratory. Their internal clock, their decay rate, slows down relative to our stationary clocks on Earth. This extended lifespan is a direct consequence of time dilation due to their high velocity. Even astronauts on the International Space Station, orbiting Earth at speeds of roughly 17,500 miles per hour, experience time ever so slightly slower than those of us on the ground. Over a typical 6-month mission, an astronaut might age a few milliseconds less than someone remaining on Earth. While this isn't enough to send them centuries into the future, it's irrefutable proof that speed bends time. Then there's gravity. Einstein's general theory of relativity, introduced in 1915, expanded on his earlier work by incorporating gravity. This theory describes gravity not as a force pulling objects together, but as a curvature in the fabric of space-time caused by mass and energy. Think of a bowling ball placed on a stretched rubber sheet. It creates a dip. If you roll a marble nearby, it will curve towards the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is curved. Similarly, massive objects like planets and stars curve spacetime, and this curvature affects the passage of time. In a stronger gravitational field, time runs more slowly than in a weaker one. This means that a clock at sea level, where Earth's gravity is slightly stronger, will tick ever so fractionally slower than a clock on top of a mountain. This effect, though minuscule on Earth, is critical for technologies like the Global Positioning System, or GPS. GPS satellites orbit at about 12,550 miles above Earth, where Earth's gravitational pull is weaker. According to general relativity, clocks on these satellites should run faster than clocks on Earth's surface. At the same time, due to their high speed, special relativity dictates their clocks should run slower. The combined effect is that the clocks on GPS satellites gain about 38 microseconds, millionths of a second, per day relative to clocks on Earth. While this might sound trivial, if these corrections weren't made, GPS systems would accumulate errors of about 7 miles per day, rendering them useless for precise navigation. So, every time you use your phone to find directions, you're experiencing a direct application of Einstein's time-bending physics. These everyday examples of time dilation, whether due to speed or gravity, demonstrate that bending time isn't just a theoretical curiosity, it's a verified reality, subtly shaping the universe around us, and something our technology already interacts with, even if we can't yet harness it to travel to distant eras. The magnitude of these effects, however, is directly proportional. To the extremes of speed and gravity involved, to achieve any truly noticeable time travel, we would need to push those boundaries far beyond anything our current technology can dream of. Having explored the subtle, yet scientifically verified, reality of time dilation due to speed and gravity, our curiosity naturally pushes us towards more extreme scenarios. If time can indeed be bent, how far can that bending go? Can it be twisted so severely that it loops back on itself or creates shortcuts through the vast expanse of space-time? Here, we venture into the realm of theoretical physics, where mathematical solutions to Einstein's equations suggest possibilities that are as mind-bending as they are currently impossible to achieve with technology. One of the most captivating and frequently discussed theoretical concepts is the wormhole. Imagine our universe, space-time, as a vast, flat sheet. If you want to get from one point on this sheet to another far away, you have to travel across the surface. Could fold the sheet, bringing those two distant points together, and then punch a hole through, creating a shortcut. That's the essence of a wormhole, a hypothetical tunnel or bridge through space-time that could connect to widely separated regions of the universe, or even to different points in time. The very idea suggests a pathway to interstellar travel that bypasses the light-year distances, and perhaps even a means of temporal displacement. Wormholes, also known as Einstein-Rosen bridges, are solutions to the equations of general relativity. However, the conditions required for their existence, and more importantly, for their stability and traversability, are incredibly demanding. Most theoretical models suggest that a traversable wormhole would require the existence of exotic matter, a hypothetical substance with negative energy density. This isn't just matter that's very cold or very dense. It's something that would effectively repel gravity, acting in direct opposition to everything we know about normal matter. Such exotic matter has not been observed in nature, and whether it can even exist, let alone be created and controlled, is a monumental question. Even if wormholes were found or created, keeping them open long enough for anything or anyone to pass through, and preventing them from collapsing instantaneously, presents another layer of insurmountable physical challenges. Then there are concepts like closed time-like curves, or CTCs. These are perhaps the closest theoretical analog to traditional time travel as seen in fiction, where one could, in principle, journey into their own past. CTCs are specific paths through space-time that loop back on themselves, meaning that an object traveling along such a path would return to an earlier point in its own history. Certain theoretical space-time geometries, such as those that might exist near rapidly spinning, infinitely long cylinders, a Tipler cylinder, or within highly specific arrangements of black holes, could potentially allow for CTCs. The conditions needed to create such a geometry are so extreme and physically implausible that they likely reside only in mathematical equations, not in the real universe. They also introduce the infamous grandfather paradox, the logical contradictions that arise if one were to alter their own past. While physicists can construct these scenarios mathematically, the consensus is that such arrangements would either be impossible to create or would be inherently unstable, preventing any actual time travel to the past. The study of black holes also offers glimpses into extreme time bending. As we touched upon earlier, the immense gravity of a black hole causes profound gravitational time dilation. For an observer very close to a black hole's event horizon, the point of no return, time would pass incredibly slowly compared to someone far away. If you were to orbit just outside the event horizon of a black hole for what felt like mere minutes, years, or even centuries could pass on Earth. This is a real, albeit extreme, manifestation of time dilation. However, actually harnessing this for controlled time travel presents a series of lethal challenges. The tidal forces near a black hole would be immense, stretching and tearing apart any object or living being long before it reached a point of significant time distortion. And, of course, escaping a black hole's gravitational pull after experiencing such time dilation is by definition impossible once you cross the event horizon. Finally, there's the bewildering world of quantum mechanics, which governs the universe at its smallest scales. While quantum mechanics doesn't directly speak to bending spacetime in the way relativity does, it introduces its own set of counterintuitive phenomena that challenge our classical understanding of time. Concepts like quantum entanglement, where two particles become linked regardless of the distance separating them, or quantum tunneling, where particles can seemingly pass through energy barriers, hint at a reality far stranger than our everyday experience. Some cutting-edge research in fields like four-dimensional quantum optics is exploring how light behaves in complex space-time geometries and phenomena like quantum state freezing, where a quantum state can be made to persist for longer than expected, suggests that time might behave differently at the quantum level. However, translating these microscopic quantum phenomena into macroscopic time bending for objects or people remains purely theoretical and currently has no clear pathway. The rules governing the quantum realm are so fundamentally different from the classical world we inhabit that bridging the gap for time manipulation is a colossal conceptual and technological leap. In essence, while Einstein's theories opened the door to the idea of a flexible, dynamic spacetime, the extreme scenarios that would allow for dramatic time bending are currently confined to theoretical models. They demand conditions and exotic materials that are either unknown or seemingly impossible to create with our current technological capabilities. The universe, it seems, has its own profound ways of bending time, but it holds the keys to truly significant manipulation very, very tightly. Having journeyed through the subtle and extreme theoretical aspects of time dilation and space-time curvature, we now arrive at a critical juncture, the formidable technological hurdles that stand between our current capabilities and any truly significant manipulation of time. It's one thing for the laws of physics to permit a phenomenon in theory. It's an entirely different challenge to build the machines and generate the conditions necessary to bring that theory into our tangible reality. This is where the dreams of science fiction meet the sobering demands of engineering, the primary obstacle to bending time in a noticeable way, whether for relativistic travel to the future or even more speculative past travel scenarios, is the colossal amount of energy required. As we discussed, time dilation due to speed only becomes significant as an object approaches the speed of light. To accelerate even a small object, let alone a human-crewed spacecraft, to such velocities would demand energy levels far beyond anything humanity has ever conceived or produced. For context, accelerating a single kilogram, about 2.2 pounds, to 99% the speed of light would require more energy than the entire world consumes in a year. The engineering challenge isn't just about generating that energy, but also containing it, directing it, and building materials that could withstand the forces and temperatures involved. Our most powerful rockets, fueled by chemical reactions, can achieve speeds that are still a tiny fraction of the speed of light, barely enough to escape Earth's gravity, let alone induce meaningful time dilation. Similarly, to create noticeable time dilation through gravity, we would need gravitational fields far more intense than anything in our solar system, short of a black hole. While we can use powerful electromagnets in laboratories, their gravitational effect is utterly negligible. To generate a gravitational field strong enough to bend space-time significantly, we would need to concentrate an enormous amount of mass into an incredibly small space. Consider a neutron star, which is the superdense remnant of a collapsed star. A teaspoon of neutron star material would weigh billions of tons. Even around these extreme objects, time dilation is present, but not easily harnessable for any practical purpose. Creating or manipulating such immense densities with technology, it is currently beyond the realm of possibility. We lack the means to compress matter to that degree, or to control the gravitational effects if we could, beyond the energy and mass requirements. There are profound material science challenges. Any hypothetical time-bending device or vehicle would need to withstand conditions that are unimaginable with current materials. Traveling at near-light speeds would expose a spacecraft to immense forces. Radiation and the erosion effects of interstellar dust, even sparse particles, would become like lethal bullets at such velocities, sustaining the integrity of a structure. Under the crushing gravitational pressures needed to create space-time curvature, would demand materials with properties far exceeding even the most advanced alloys and composites we have today. The exotic matter theorized to keep wormholes open also falls into this category. It's not just a matter of finding it, but of synthesizing, stabilizing, and manipulating something that defies our current understanding of normal matter. Then there's the issue of control and precision. Even if we theoretically had the energy and materials, the ability to precisely control the warping of spacetime or the navigation of temporal paths would require an understanding of quantum gravity that we simply don't possess. Our current theories of gravity general relativity break down at quantum scales, and a unified theory of everything, which would likely be necessary to truly understand and manipulate spacetime at a fundamental level, remains one of the holy grails of physics. Without this deeper understanding, any attempt to bend time would be akin to trying to build a complex computer chip with only a basic understanding of electricity. The unpredictable consequences could be catastrophic, even seemingly simpler. Proposals, like Mallet's theoretical time machine based on circulating light beams, face these insurmountable practicalities. The power of the light beam required to create even a minuscule time-warping effect would be astronomical, far exceeding the output of every power plant on Earth combined, focused into an incredibly precise configuration that defies current optics or energy containment. In essence, while the universe offers the theoretical blueprint for time bending through its very nature, the technological gap is immense. It's not just a matter of building a bigger rocket or a more powerful laser. It requires fundamentally new physics, materials, and energy sources that are currently confined to the realm of theoretical speculation. The journey from scientific theory to technological reality is often a long one, marked by incremental discoveries and revolutionary breakthroughs. For time bending, we are arguably still at the very earliest, most theoretical stages. Observing its subtle dance in the cosmos, but far from directing its choreography. All right, let's continue with the script, for can we bend time with technology? While the grand visions of time machines capable of whisking us to any point in history remain firmly in the realm of theoretical physics and science fiction, understanding of time has been profoundly shaped by real-world technologies that interact with its subtle nature. These aren't devices that warp time on a cosmic scale, but rather everyday tools that demonstrate the practical implications of Einstein's theories, reminding us that time is far more dynamic than our initial intuitions suggest. The most prominent example, one we interact with constantly, is the Global Positioning System, or GPS. Every time you pull out your smartphone to navigate to a new restaurant, find the fastest route to work, or track your morning run, you are directly engaging with a technology that accounts for the bending of time. Without precisely correcting for relativistic effects, GPS simply wouldn't work. Here's how it plays out. GPS satellites orbit Earth at an altitude of approximately 20,200 kilometers, about 12,550 miles, and travel at speeds of around 3.87 kilometers per second, about 8,680 miles per hour. Now, remember our discussion about time dilation? Two key effects are at play for these satellites. First, due to their high speed, according to Einstein's special theory of relativity, their clocks should tick slightly slower than identical clocks on Earth's surface. This relativistic time dilation amounts to about 7 microseconds, millionths of a second per day. Second, because they are further away from Earth's massive gravitational pull, they experience a weaker gravitational field. According to Einstein's general theory of relativity, clocks in weaker gravitational fields run slightly faster than those in stronger fields. This gravitational time dilation effect is much larger, causing the satellite clocks to gain about 45 microseconds per day. When you combine these two effects, the net result is that the clocks on GPS satellites gain approximately 38 microseconds, 45 minus 7 equals 38 per day, relative to clocks on Earth's surface. While a microsecond might seem infinitesimally small, light travels about 300 meters, roughly 984 feet, in 1 microsecond. So, if these time differences weren't corrected, the position calculations made by your GPS receiver would drift by about 10 kilometers over 6 miles every single day. Your navigation app would be wildly inaccurate, rendering it useless for guiding you through city streets or even across continents to ensure accuracy. The atomic clocks on board GPS satellites are meticulously designed to tick at a slightly slower rate before launch. Anticipating these relativistic effects, they are precisely calibrated so that once in orbit, the combined effect of speed and gravity causes them to tick at exactly the same rate as clocks on Earth. Furthermore, the ground control stations continuously monitor and make minute adjustments to the satellite clocks to maintain this astonishing precision. So, GPS isn't just about satellites and signals, it's a living, breathing testament to the reality of time dilation. Built on our understanding of how gravity and speed bend time beyond GPS, our understanding of relativistic time effects is crucial in other areas of cutting-edge technology and fundamental research. High-energy particle accelerators, like the Large Hadron Collider, LHC, at CERN, accelerate subatomic particles to speeds incredibly close to the speed of light. As mentioned earlier, unstable particles created in these accelerators, or even naturally occurring cosmic ray muons, are observed to have extended lifetimes from our perspective. Their internal clocks tick slower, allowing them to travel much farther before decaying than they would if they were stationary. This isn't just a curious observation, it's a fundamental aspect of particle physics experiments, allowing scientists to study these elusive particles more effectively, even in the realm of precise timekeeping itself. Our atomic clocks, which are the most accurate timekeeping devices known, must account for these subtle relativistic effects. For example, clocks located at different altitudes, even within the same building, will tick at slightly different rates due to the minuscule differences in Earth's gravitational pull. While not practically significant for daily life, for experiments pushing the boundaries of precision measurement, these effects become detectable and must be considered. These technological applications demonstrate that while we might not be building a flux capacitor to jump through eras, we are already interacting with the relativistic nature of time. Our technology doesn't create the bending of time, but rather it relies on understanding and accounting for the universe's inherent time-bending properties to function accurately. It grounds the abstract theories of Einstein in concrete, everyday utility, making the once unfathomable concept of relative time an undeniable part of our technological landscape. It also highlights the extreme sensitivity of time, revealing that even small changes in speed or gravitational potential can leave their subtle, yet measurable, mark on the flow of moments. Having explored the ways our technology already interacts with time dilation, proving that time is indeed a flexible dimension, we now step further into the realm of theoretical physics. Here, scientists armed with mathematics and audacious imagination explore concepts that push the very boundaries of what might be possible, even if the technological means to achieve them are currently unimaginable. These ideas often involve manipulating space-time in ways far more dramatic than simply experiencing different rates of time flow. One of the most intriguing and often misunderstood concepts is the idea of time travel to the past, while time dilation allows for a kind of travel to the future, relative to someone else, by moving fast or being near a strong gravitational source. Journeying into one's own past presents profound, logical, and physical challenges. The most famous of these is the grandfather paradox, where one could theoretically go back in time and prevent their own existence, creating a logical contradiction. Many physicists believe that such paradoxes imply that true past-time travel it is impossible, or that, if it were possible, the universe would have mechanisms to prevent such paradoxes from occurring. Some theories, like the Nabokov self-consistency principle, suggest that if time travel to the past were possible, any actions taken by a time traveler would already be part of the past's history, thus preventing paradoxes. Your actions in the past would simply be what always happened, preventing any contradictions. Beyond the paradoxes, the theoretical mechanisms for past-time travel are equally challenging. We touched upon closed time-like curves, CTCs, earlier. These are paths through space-time that loop back on themselves, allowing an object or person to return to an earlier point in their own timeline. Mathematically, CTCs can emerge from solutions to Einstein's field equations under extreme conditions. For instance, some models involve the spacetime around rapidly spinning, infinitely long cylinders known as Tipler cylinders or configurations of exotic matter. However, the conditions required to create such spacetime geometry is infinite length, impossible energy densities, or the need for negative energy matter are so far beyond our capabilities and possibly beyond what's physically allowed. They are generally considered non-starters for practical time travel. It's more of a mathematical curiosity than a blueprint for a machine. Another fascinating, albeit highly speculative concept related to time manipulation is the idea of manipulating space-time to create warp drives. While not directly about time travel in the traditional sense, a warp drive, like the Alcubierre drive, proposes a method of faster-than-light travel by effectively bending space-time around a spacecraft. Instead of the spacecraft itself moving at superluminal speeds, it would remain stationary within a warp bubble of space-time that contracts in front of it and expands behind it. If such a drive were possible, the time experienced by someone inside the bubble would be significantly different from the time experienced by an external observer, creating a form of extreme time dilation relative to external points. However, like wormholes, warp drives also require vast amounts of exotic matter with negative energy density to create and sustain the warp bubble. The energy requirements are also astronomical, far exceeding the mass energy equivalent of entire planets. Then there's the intriguing work of scientists, like Ronald Mallet. He has dedicated his career to exploring the theoretical possibility of time travel based on Einstein's general theory of relativity. Mallet's models propose that a rotating black hole can twist or drag space-time around it, and he suggests that circulating beams of light, if powerful enough, could mimic this effect on a smaller scale. In his theory, an intense circulating laser beam could create a similar time warp effect, potentially leading to the formation of a closed time-like curve within the region of the light beam. If successful, this would allow for time travel into the past, specifically to the point when the time machine was first activated. However, the energy density of the light beam required would be astronomical, so immense that it would likely collapse into a black hole before achieving the desired effect. And the precision needed to control such a phenomenon is currently beyond comprehension. It's a testament to how far theoretical physics can stretch our imaginations, even when technological implementation is currently impossible. The challenges with these theoretical proposals are not just engineering ones. They often butt up against fundamental physics. The need for exotic matter, the stability issues of wormholes and CTCs, and the energy requirements that far surpass the energy output of stars all point to the current understanding that while space-time is bendable, the universe seems to have built-in safeguards that prevent us from bending it into paradoxes or shortcuts that violate causality. It's a humbling thought, but also an inspiring one. These theoretical explorations, despite their current impossibility, push the boundaries of our understanding of physics. They force us to confront the deepest questions about the nature of time, causality, and the very structure of the universe. While we may not be building these machines anytime soon, the intellectual journey of exploring them continues to refine our models of reality and might, in unexpected ways, lead to new discoveries in energy, materials, or space-time physics that we can't even foresee today. For now, the past remains unreachable, and significant leaps into the future only occur at speeds and gravitational strengths that are far beyond our technological grasp. Our exploration of time-bending, from its subtle presence in everyday technology to its wilder theoretical manifestations, inevitably leads us to the practical, if currently insurmountable, technological limitations that define our present reality. The gap between what physics suggests might be possible and what our engineers can actually build is vast, measured not just in energy units and material strength, but also in fundamental scientific understanding yet to be achieved. Most immediate and glaring limitations is energy. To induce noticeable time dilation through speed, an object must approach a significant fraction of the speed of light. Consider the energy required for this. Even for a tiny spacecraft, accelerating it to, say, 90% of the speed of light would demand energy levels equivalent to many years of the entire world's current energy consumption. Our most powerful existing energy sources, nuclear fission reactors, fossil fuels, or even renewable sources, produce only a minuscule fraction of what would be needed for such a feat. Fusion power, often hailed as the energy source of the future, is still in its developmental stages, and even if perfected, would likely not generate power on the scale required for relativistic space travel. We simply do not have the capacity to generate, store, or efficiently convert energy on the scale necessary to impart such extreme velocities to macroscopic objects. Similarly, manipulating time through gravity runs into even more profound energy and mass constraints. To create a gravitational field intense enough to significantly warp spacetime and cause measurable time dilation, one would need to concentrate an unimaginable amount of mass into a tiny region. Think about the densest objects we know: neutron, stars, or black holes. These are formed from the collapse of stars far more massive than our Sun, compressing matter to extraordinary densities. A teaspoon of neutron star material could weigh billions of tons. Replicating even a tiny fraction of this density with technology is utterly beyond our current capabilities. We don't have the means to compress matter to such extremes, nor to sustain it. The theoretical exotic matter with negative energy density required for stable wormholes or warp drives is even more problematic, as it is not known to exist in our universe, and if it did, manipulating it would require physics far beyond our current grasp. Then there's the monumental challenge of materials science. Any technology designed to bend time, whether through extreme speed or gravity, would be subjected to forces, temperatures, and pressures that no known material could withstand. A spacecraft traveling at near-light speeds would encounter interstellar dust and gas particles with kinetic energies equivalent to nuclear explosions, quickly eroding or disintegrating the craft. Building a structure capable of containing the energy of a mini-star or withstanding the stresses of artificially generated gravitational wells would require materials with properties that far exceed steel, titanium, or even advanced carbon composites. We'd need materials that are incredibly light, impossibly strong, resistant to extreme temperatures, and perhaps even capable of adapting to spacetime distortions. Such materials exist only in theoretical concepts, not in our metallurgy labs. Furthermore, our understanding of spacetime itself, particularly at the quantum level, is incomplete. General relativity describes gravity and spacetime on large scales, but it doesn't fully reconcile with quantum mechanics, which governs the universe at its smallest dimensions. This lack of a unified theory of quantum gravity means we don't fully understand the fundamental nature of spacetime, especially under extreme conditions. Without this complete picture, attempting to precisely manipulate something as fundamental as time would be akin to performing delicate brain surgery without a full understanding of neurology. Any hypothetical device attempting to warp time would need incredibly precise controls, and without a deeper theoretical framework, unintended and potentially catastrophic consequences would be a constant risk. Even for less dramatic theoretical concepts like Dr. Ronald Mallett's proposal for using circulating light beams to create CTCs, the technological hurdles are immense. His models require laser beams of such immense power and density that they would effectively become light-based black holes, along with a precision in manipulating spacetime that is currently science fiction. The sheer energy involved and the stability issues of trying to twist spacetime make such a device currently unrealizable. In essence, humanity is still in its infancy when it comes to truly manipulating the fundamental forces and structures of the universe. We can build complex machines, harness immense power, and send probes to distant planets. But bending time in any significant way would require a leap in physics, energy production, and material science that is so profound it amounts to a fundamental shift in our civilization's technological paradigm. It's not simply a matter of scaling up existing technologies. It demands breakthroughs in areas we currently only theorize about. For the foreseeable future, the bending of time remains largely a cosmic phenomenon that we can observe and account for, but not actively control or harness for our own temporal journeys. While the cutting-edge theories and immense technological hurdles dominate discussions about bending time, it's crucial to acknowledge that our current understanding and everyday experiences already offer subtle glimpses into time's flexible nature. We may not have a time machine parked in our garage, but the principles of relativity, which underpin the concept of time manipulation, are woven into the very fabric of our modern technological landscape. Far from being abstract equations, they are actively accounted for to make essential systems function, demonstrating that time, in its relativistic sense, is indeed pliable. Consider, for instance, the sheer precision required for global positioning system GPS technology. When you navigate with your phone, tablet, or car, you're relying on a network of satellites orbiting Earth. These satellites contain incredibly accurate atomic clocks, which synchronize with receivers on the ground. For GPS to provide pinpoint accuracy, allowing you to find a specific address or even track your precise location on a hiking trail, these clocks must be synchronized to an astonishing degree, down to mere nanoseconds, billionths of a second. Without correcting for relativistic effects, this precision would quickly unravel, as we touched upon earlier. Two types of time dilation affect GPS satellites. Special relativistic time dilation, due to their high orbital speed, approximately 14,000 kilometers per hour or 8,700 miles per hour. The clocks on GPS satellites tick slightly slower than identical clocks on Earth. This effect alone would cause them to lose about 7 microseconds per day, general relativistic time dilation. Because the satellites are further from Earth's center, they experience a weaker gravitational field. In a weaker gravitational field, clocks tick faster. This effect causes them to gain about 45 microseconds per day. The net result is that the clocks on GPS satellites gain about 38 microseconds for 5738 every day compared to clocks on Earth. If engineers didn't account for and correct this discrepancy, your GPS receiver would accumulate errors of roughly 10 kilometers over 6 miles per day. The navigation system would be completely useless. To counteract this, the atomic clocks on GPS satellites are designed to run slightly slower before launch, so that once in orbit, the combined relativistic effects cause them to tick at the same rate as ground-based clocks. This is a real-world, everyday example of our technology actively compensating for the universe's inherent time bending. Beyond GPS, our understanding of relativistic time is crucial in high-energy physics experiments. Particle accelerators, such as the Large Hadron Collider (LHC) at CERN, accelerate subatomic particles to speeds extremely close to the speed of light. Many of these particles, like muons, are naturally unstable and have very short lifespans. However, when accelerated to such incredible velocities, their internal clocks tick slower from our perspective. This means they effectively live longer than they would if they were stationary. This extended lifespan allows scientists to study them for a longer duration, providing critical insights into the fundamental building blocks of the universe. The observed longevity of these particles is a direct and repeatable confirmation of special relativistic time dilation. If our calculations didn't account for time dilation, our understanding of particle decay rates and the very nature of matter at extreme speeds would be fundamentally flawed. Even in the development of the most accurate timekeeping devices on Earth, the atomic clocks that define international time standards, relativistic effects must be considered. While the gravitational differences across a few meters on Earth's surface are tiny, for ultra-precise atomic clocks, even the difference in height between two clocks can result in a detectable difference in their ticking rates. Higher elevation, experiencing slightly weaker gravity, will tick marginally faster than a clock at a lower elevation. These effects are not significant for daily human experience, but for the cutting edge of scientific measurement, they become relevant and are accounted for. In the pursuit of ever greater precision, these examples highlight that bending time isn't just an abstract concept for distant galaxies or theoretical wormholes. It's a fundamental property of our universe that our most sophisticated technologies are built upon, and which we implicitly acknowledge every time we use a GPS device or study a particle in an accelerator. While we may not be creating dramatic temporal shifts, we are certainly using technology to measure, predict, and compensate for time's natural flexibility. This continuous interaction between technology and the relativistic nature of time underscores just how much our understanding of the universe has advanced, transforming what was once unimaginable into a cornerstone of modern engineering. It's a quiet form of time bending, but profound nonetheless. While the theoretical concepts of wormholes and warp drives tantalize us with visions of extreme time manipulation, and GPS demonstrates time bending's subtle reality, the current frontier of technological exploration focuses on pushing the boundaries of what's practically achievable with our existing physics. This often involves manipulating light and matter in ways that, while not directly time travel, hint at a deeper control over the fabric of reality. One fascinating area is the manipulation of light itself. Light, or photons, are massless particles that always travel at the speed of light in a vacuum. According to special relativity, time effectively stops for a photon. While we can't make anything with mass reach the speed of light, scientists are finding ways to slow light down or even stop it entirely using exotic states of matter. For instance, researchers have used ultra-cold atomic gases, known as Bose-Einstein condensates, to slow pulses of light to bicycle speeds, or even bring them to a complete halt and then re-emit them. This isn't stopping time for observers, but it demonstrates an incredible level of control over the propagation of information, which is intimately tied to the flow of causality and time. While the immediate applications are in quantum computing and information storage, such experiments are foundational for understanding how light interacts with matter at the most profound levels, perhaps one day leading to insights into manipulating space-time itself. Another intriguing field is quantum mechanics, which, as we touched upon, presents a very different picture of time at the subatomic scale. In the quantum realm, phenomena like superposition, a particle existing in multiple states at once, and entanglement to particles linked instantaneously, regardless of distance, defy our classical intuition. While these don't offer a direct path to time travel, they hint at a reality where classical notions of sequential time might not always apply. Some theories explore how quantum events might influence the past, not by changing it, but by determining the outcome of an event that has already occurred in a classically defined timeline. This is known as retrocausality, a highly debated concept that suggests a quantum measurement in the present could affect the properties of a particle in the past. It doesn't mean changing history, but rather that the choice made in the present could determine which potential past was realized. Again, this is not time travel as we imagine it, but it's a testament to the strange dance between time and quantum reality. Beyond the fundamental physics, engineering ingenuity is constantly pushing limits in ways that, while not directly time-bending, are often inspired by these theoretical concepts. For instance, the development of incredibly powerful laser systems aims to create extreme energy densities. While falling short of the astronomical levels needed for a Mala-type time machine, these lasers can create temporary extreme states of matter and generate pressures that exist only in stellar cores. Studying these conditions helps us understand the universe at its most violent and extreme, potentially offering indirect insights into energy generation and matter manipulation that could be relevant to space-time distortion in the far future. Moreover, the drive to achieve faster-than-light FTL communication or travel, even if not through warp drives, often involves theoretical pathways that would inherently interact with time. If FTL travel were possible, special relativity dictates that it would also allow for time travel to the past, leading back to the paradoxes we discussed. This is why many physicists believe that FTL travel, like past-time travel, is either impossible or requires entirely new physics that we don't yet comprehend. Technologies like quantum communication, which exploits entanglement, allow for instantaneous correlation of information, but not faster-than-light transmission of information, thus preserving causality and preventing time paradoxes. Ultimately, current technology's interaction with time is more about precise measurement, compensation for relativistic effects, and the exploration of fundamental principles at quantum and extreme energy scales. We are building increasingly sensitive atomic clocks, conducting experiments that verify time dilation, and pushing the boundaries of our understanding of light and matter. These advancements, while not delivering a time machine, are incrementally expanding our grasp on the universe's most elusive dimension. Each successful experiment, each precise calculation, brings us a little closer to understanding the true nature of time, and with that, perhaps the most profound ways it can, or cannot, be influenced. All right, let's conclude our script on Can We Bend Time with Technology, with a final section focusing on the future outlook and the enduring fascination with this concept. As we've explored the intricate relationship between technology and time, from the subtle daily proofs of time dilation in GPS to the far-flung theoretical concepts of wormholes and warp drives, it becomes clear that bending time is not a simple, straightforward proposition like building a faster car. It delves into the very fabric of the universe, challenging our intuitive perceptions and pushing the boundaries of scientific inquiry. So, what does the future hold for our ability to influence time, and why does this quest continue to captivate us so profoundly? The immediate future of technology's interaction with time will likely continue along the lines of increasing precision and deeper understanding, rather than dramatic temporal leaps. We can expect even more accurate atomic clocks, perhaps clocks, so precise that they could detect the gravitational time dilation from a mere foot of elevation difference, or clocks that maintain perfect synchronization across vast distances with even less drift. Such advancements, while not enabling time travel, are crucial for next-generation navigation systems, ultra-secure communication networks, and fundamental physics experiments that probe the universe's most subtle effects. This pursuit of precision is a quiet, continuous form of time-bending that our technology is constantly refining. Research into quantum gravity remains a major frontier. If physicists ever succeed in developing a unified theory that reconciles general relativity with quantum mechanics, it could unlock entirely new insights into the nature of spacetime. This theoretical breakthrough might reveal new ways that time can be influenced or even fundamentally re-understood, moving beyond our current models. However, such a theory is likely decades, if not centuries, away, and its practical implications for time manipulation are impossible to predict. It might confirm that certain types of time travel are truly impossible, or it might open up entirely new, unforeseen avenues. Beyond the purely scientific, the enduring fascination with bending time highlights a deeply human desire to control destiny, to revisit the past, or to glimpse the future. This yearning is rooted in our limited experience of time as an irreversible, unidirectional flow. We want to correct mistakes, savor lost moments, or prepare for what's to come. This emotional and philosophical pull ensures that even if scientific consensus firmly states that time machines are impossible, the idea of bending time will continue to inspire artists, writers, and dreamers. It serves as a powerful metaphor for our hopes and regrets, and for the limits of our control over life's trajectory. Ultimately, whether we can bend time with technology depends entirely on what we mean by bending. If we mean subtly influencing its rate of passage, as demonstrated by GPS and particle accelerators, then yes, we already do. Our technology is built upon this relativistic understanding, constantly adapting to time's natural flexibility. If we mean creating traversable wormholes, building warp drives, or journeying into our own past, then the answer, with our current understanding of physics and technology, is a resounding no. The energy requirements are prohibitive, the material science is non-existent, and the theoretical physics points to fundamental paradoxes or the need for currently unobserved exotic matter. Perhaps the most profound takeaway from this exploration isn't about building a time machine, but about our journey of discovery itself. The very act of asking, can we bend time, has pushed us to develop a deeper, more nuanced understanding of space-time, gravity, and the fundamental nature of reality. It has led to technological innovations that rely on these insights, even if they don't fulfill the grander science fiction. Dreams. The universe, in its elegant complexity, continues to hold many secrets. Time, that most mysterious of dimensions, is clearly more flexible than we once imagined. While we might not be orchestrating dramatic temporal shifts, our continuous scientific inquiry and technological advancement allow us to observe, measure, and increasingly appreciate the subtle, inherent ways in which time truly does bend. And in that ongoing wonder, there is a profound satisfaction, a reminder that the greatest journeys are often those of understanding the cosmos itself. The concept of time, as a fourth dimension interwoven with the three dimensions of space, is a cornerstone of modern physics. Yet it was not always so. For centuries, the prevailing view, largely influenced by Isaac Newton, was that time was an absolute and universal constant, ticking away uniformly for everyone, everywhere. It was seen as a fixed, immutable backdrop against which all events unfolded, independent of any observer or physical process. In this Newtonian universe, a second was always a second, no matter where you were or how fast you were moving. This intuitive understanding, aligning with our everyday experience, shaped scientific thought for over 2 centuries. However, the late 19th and early 20th centuries brought forth new observations and ideas that began to challenge this rigid framework. Experiments, particularly those dealing with the nature of light, revealed inconsistencies with the Newtonian view. It was in this intellectual climate that Albert Einstein, with his groundbreaking theories of relativity, completely revolutionized our understanding. In 1905, his special theory of relativity introduced the radical idea that time is not absolute, but relative. This theory posited two fundamental principles. First, that the laws of physics are the same for all observers in uniform motion, i.e., not accelerating. And second, that the speed of light in a vacuum is constant for all observers, regardless of their own motion or the motion of the light source. These seemingly simple postulates led to profound and counterintuitive consequences. If the speed of light is always constant, then something else must be flexible. That something, Einstein showed, was time itself, along with space. For the speed of light to remain constant for all observers, time must slow down or speed up, and distances must contract or expand, depending on the observer's relative motion. This phenomenon is known as time dilation and length contraction. It meant that a second for one observer could be a different duration for another observer moving at a high relative speed. A decade later, in 1915, Einstein expanded his ideas with the general theory of relativity, which incorporated gravity into this flexible space-time framework. Rather than seeing gravity as a force, Einstein proposed that massive objects like planets and stars warp the fabric of space-time around them, much like a bowling ball creating a dip on a stretched rubber sheet. It's this curvature of space-time that we perceive as gravity. And crucially, this curvature also affects the passage of time. In a stronger gravitational field, time slows down, while in a weaker field, it speeds up. This meant that gravity itself could bend time together. These theories painted a picture of a dynamic, interwoven spacetime where time is no longer a fixed, external clock, but an intrinsic part of the universe's geometry capable of being stretched, squeezed, and, in a very real sense, bent by speed and mass. This was a radical departure from centuries of scientific thought and opened up entirely new avenues for understanding the cosmos, including the perplexing possibility of manipulating time itself. While the dramatic leaps of science fiction remained distant, the underlying principle of time's flexibility became a cornerstone of modern physics. Verified by countless experiments and observations over the subsequent decades, this new understanding laid the groundwork for contemplating if and how technology might eventually interact with these principles. It shifted the question from a philosophical, if time can be bent, to a scientific, how does time bend, and can we harness that knowledge? Our journey continues by examining the measurable, subtle ways our technology already demonstrates this bending, even if we don't realize it in our daily lives. One of the most practical and astonishing proofs of time's flexibility lies in our everyday technology, specifically the Global Positioning System, or GPS. While it might seem like a simple matter of satellites beaming down signals, the accuracy of GPS relies fundamentally on accounting for the very time-bending effects predicted by Einstein's theories of relativity. Without these precise relativistic corrections, your navigation app would send you miles off course within hours, rendering the entire system useless. Think about how GPS works: a network of satellites orbits Earth, each equipped with extremely accurate atomic clocks. These satellites continuously broadcast signals containing their exact location and the precise time the signal was sent. Your GPS receiver, in your phone, car, or other device, picks up these signals from multiple satellites, calculates the time difference between when the signal was sent and when it was received, and uses that information, combined with the known positions of the satellites, to triangulate your exact location on Earth. For this to work with the accuracy we expect, down to a few meters, the timing has to be incredibly precise, measured in billionths of a second or nanoseconds. Now, here's where time bending enters the picture. The GPS satellites are not stationary. They orbit Earth at a speed of approximately 14,000 kilometers per hour, about 8,700 miles per hour. according to Einstein's special theory of relativity, which deals with relative motion. Clocks that are moving tick slower than clocks that are stationary. For the GPS satellites, this means their onboard atomic clocks, due to their high velocity, experience a time dilation effect that makes them run about 7 microseconds millionths of a second. Slower per day compared to a stationary clock on Earth, but that's only half the story. The satellites are also orbiting at an altitude of about 20,200 kilometers, 12,550 miles, above Earth's surface. At this higher altitude, the gravitational pull from Earth is weaker than it is on the surface. Einstein's general theory of relativity, which describes how mass and energy warp spacetime, tells us that clocks tick faster in weaker gravitational fields and slower in stronger ones. So, due to the weaker gravity at their altitude, the clocks on the GPS satellites actually run about 45 microseconds faster per day than clocks on Earth's surface. When you combine these two relativistic effects, the clocks running slower due to speed, 7 microseconds day, and faster due to weaker gravity, plus 45 microseconds day. The net result is that the satellite clocks gain approximately 38 microseconds. 45 minus 7 equals 38 every single day relative to clocks on the ground. To put that into perspective, light travels almost 11.4 kilometers, 7 miles, in 38 microseconds. If these corrections weren't made, the errors in GPS positioning would accumulate to about 10 kilometers over 6 miles daily, making the system utterly unreliable for navigation or any other precise application. To counteract this, the atomic clocks on board the GPS satellites are deliberately designed and set to tick at a slightly slower rate before they are launched into orbit. This pre-compensation ensures that once they are in their operational orbit, the combined effects of special and general relativistic time dilation cause them to tick at precisely the same rate as the ground-based atomic clocks. Furthermore, ground control stations continuously monitor and make minute adjustments to the satellite clocks to maintain this astonishing level of synchronization. This isn't a theoretical exercise. It's a daily fundamental operation. Every time your phone instantly tells you where you are, it's a direct, practical demonstration that time is not absolute, that it can be bent by speed and gravity, and that our technology has learned to precisely account for this cosmic flexibility. GPS is a powerful, undeniable testament to the reality of relativistic time dilation, proving that the universe is far stranger and more dynamic than our everyday experiences might suggest. All right, let's continue with the script for Can We Bend Time with Technology? Beyond the everyday practicality of GPS, the principles of time dilation are critical in the cutting-edge world of high-energy physics. Here, scientists aren't just observing time's flexibility, they're actively creating conditions where relativistic effects are profoundly dramatic, enabling discoveries that deepen our understanding of the universe's most fundamental building blocks. These massive machines, often stretching for kilometers underground, are perhaps the most powerful time-bending technologies we possess, though their purpose isn't to send us on a temporal journey, but to unveil the secrets of matter and energy. Consider the Large Hadron Collider, LHC, at CERN, on the border of Switzerland and France. This is the world's largest and most powerful particle accelerator, a 27-kilometer, 17-mile ring buried deep beneath the ground, where protons are accelerated to nearly the speed of light, specifically to about 99.999999% the speed of light. At these incredible velocities, the effects of special relativistic time dilation become not just measurable, but overwhelmingly apparent and absolutely essential for the experiments conducted. Many of the subatomic particles produced and studied in these accelerators are inherently unstable, meaning they spontaneously decay into other particles after a very short lifespan. Take, for example, a particle called a muon, when at rest in a laboratory, has an average lifespan of just about 2.2 microseconds, 2.2 millionths of a second. If you were to create a muon and watch it, it would decay in the blink of an eye. If these particles didn't experience time dilation, they would decay almost immediately after being created in the accelerator or upon hitting a detector, making them incredibly difficult, if not impossible, to study. However, when muons are accelerated two near-light speeds in the LHC. Their internal clock, the rate at which they decay, slows down dramatically from the perspective of a stationary observer in the lab. Due to time dilation, a muon traveling at such extreme speeds might have its observed lifespan extended by a factor of hundreds or even thousands. This means a muon that would normally decay after traveling only a few hundred meters might now travel for several kilometers before decaying. This extended life allows physicists to guide these particles through detectors, collect data on their properties, and analyze their decay products. Without this real and measurable time dilation, much of modern particle physics, including the discovery of particles like the Higgs boson, would be impossible. The very design and operation of these accelerators fundamentally rely on these relativistic time-bending effects. It's not just man-made accelerators that demonstrate this. Naturally occurring phenomena, like cosmic rays, provide another powerful example. Cosmic rays are high-energy particles that constantly bombard Earth from space. When these particles strike the Earth's upper atmosphere, they create showers of secondary particles, including muons. These muons are generated at altitudes of many kilometers above Earth's surface. If they didn't experience time dilation, very few of them would survive long enough to reach detectors on the ground. Given their incredibly short proper lifespan of 2.2 microseconds, yet we detect a significant flux of muons at sea level. The only explanation for their survival and ability to travel such distances is that their internal clocks have been slowed down dramatically due to their relativistic speeds, allowing them to traverse thousands of meters in what, for them, feels like mere nanoseconds. These real-world examples in high-energy physics are powerful affirmations of Einstein's theories. They show that time-bending isn't a theoretical abstraction or a distant fantasy. It's an observable, measurable, and technologically critical phenomenon. Our instruments are sophisticated enough to not only detect these changes in time's flow, but to utilize them as an integral part of scientific discovery. While we are not using these accelerators to send humans into the future, they undeniably demonstrate that the rate at which time passes is not fixed, but is dynamically influenced by motion, exactly as relativity predicts. All right, let's continue with the script for Can We Bend Time with Technology? While the confirmed relativistic effects are fascinating, the deeper scientific inquiry into bending time pushes into the realm of extreme theoretical physics, where the universe's most enigmatic phenomena might offer clues. Here, discussions often revolve around objects so dense or concepts so abstract that they make the effects observed in particle accelerators seem trivial. We're talking about black holes and the mathematical constructs they inspire, which are the ultimate natural time benders we know of. A black hole is not merely a superdense object. It's a region of space-time where gravity is so intense that nothing, not even light, can escape. This is due to the extreme warping of space-time caused by an enormous amount of mass compressed into an incredibly small volume, often originating from the collapsed core of a massive star. The boundary beyond which escape is impossible is called the event horizon. Now, within this extreme environment, time behaves in truly mind-bending ways, consistent with Einstein's general theory of relativity. For an observer located very close to the event horizon of a black hole, time would appear to pass incredibly slowly compared to an observer far away. Imagine an astronaut orbiting safely just outside a black hole's event horizon, sending signals back to Earth. To the astronaut, their clock might tick normally, and they might experience minutes or hours. But to the distant observer on Earth, those minutes or hours for the astronaut could translate into years, decades, or even centuries. The light signals from the astronaut would appear increasingly redshifted, stretched out, and their actions would seem to unfold in extreme slow motion, eventually appearing to freeze entirely as they approached the event horizon. This is gravitational time dilation taken to its absolute extreme. Theoretically, if one could somehow survive and spend time near a black hole's event horizon, then escape, they would effectively have traveled far into the future relative to those who remained far away. However, the practicalities are lethal. The tidal forces close to a black hole are immense, meaning the gravitational pull would be significantly stronger on the part of your body closest to the black hole than on the part farthest away. This difference in pull would stretch any object, including a human body, or even the strongest spacecraft, into a long, thin, spaghetti-like strand before it ever reached the event horizon, a process grimly known as spaghettification. If you could survive the tidal forces, crossing the event horizon is a one-way trip. Nothing can escape, meaning any future travel would be permanent. Beyond black holes, theoretical physics sometimes explores even more speculative concepts like naked singularities. A singularity is the infinitely dense point at the heart of a black hole in most scenarios. This singularity is hidden behind an event horizon. However, some theoretical solutions to Einstein's equations suggest that a singularity might exist without an event horizon. Hence, naked. If a naked singularity were to exist, it could potentially allow for direct interaction with conditions of extreme spacetime curvature without the absolute barrier of an event horizon, possibly opening pathways to even more extreme time distortions, or even closed time-like curves, CTCs, which, as discussed, imply time travel to the past. However, the existence of naked singularities is highly debated among physicists, with many believing that cosmic censorship hypotheses prevent them from forming in our universe, thereby safeguarding causality. These extreme gravitational scenarios are not about technology creating time bending, but rather about the universe's most powerful natural phenomena exhibiting it in its most dramatic forms. Our technology can observe these effects, for example, through X-ray and radio astronomy detecting the accretion disks around black holes, or gravitational wave detectors sensing their mergers, but it is currently, and likely for the foreseeable future, utterly incapable of replicating or harnessing such conditions for any practical time manipulation. They serve as a reminder of the incredible elasticity of spacetime and the profound implications of Einstein's genius, pushing our imagination to its very limits. And so, here at the end of our gentle journey through the science of time, from the subtle daily proofs in our technology to the mind-bending theories of the cosmos, we return to our initial question. Can we bend time with technology? The answer, as we've found, is far more nuanced and perhaps more wondrous than a simple yes or no. We've learned that time is not the rigid, unyielding river we once imagined. Thanks to Albert Einstein's revolutionary insights, we now understand that time is inextricably woven with space, forming a flexible fabric called spacetime. This fabric can be stretched, compressed, and subtly influenced by two primary forces, speed and gravity. Our technology doesn't just theorize about this, it actively demonstrates it. Every time a GPS satellite beams down its precise location, it does so because engineers have meticulously accounted for the tiny yet crucial time dilation effects caused by its velocity and distance from Earth's gravity. Without these corrections, our navigation systems would be useless, drifting by miles each day. Similarly, in the colossal rings of particle accelerators, subatomic particles live longer than they should, their internal clocks slowed by speeds approaching light, a powerful testament to special relativistic time dilation. These are not science fiction fantasies. They are the observable, measurable realities of our universe, and our technology has learned to navigate them with astonishing precision. This bending of time is subtle, an incremental shift rather than a dramatic leap. It allows for a form of one-way travel to the future relative to an observer who experiences time at a faster rate, but it's not the kind of jump depicted in movies. When we venture into the more speculative realms, like the immense gravitational fields near black holes, or the mathematical constructs of wormholes and closed time-like curves, the theoretical possibilities become far more dramatic. Black holes are the universe's ultimate natural time benders, where time can slow to a near standstill for an observer close to the event horizon relative to someone far away. However, harnessing such extremes presents insurmountable challenges, including lethal tidal forces and the absolute barrier of the event horizon. Wormholes and CTCs, while theoretically intriguing as shortcuts through spacetime or pathways to the past, currently demand the existence of exotic matter with negative energy, a substance not known to exist, and energy levels beyond anything imaginable. The truth is, our current technological limitations are immense. We lack the energy sources to accelerate anything substantial to near-light speeds. We cannot create or sustain the extreme gravitational densities required to significantly WARP, spacetime. Our material science is generations away from developing structures that could withstand such conditions, and crucially, our fundamental understanding of quantum gravity, which would be necessary to truly manipulate spacetime at its deepest level, is still incomplete. So for now, the fantastical visions of time machines capable of whisking us to any point in history remain firmly in the realm of dreams and theoretical physics. The universe, it seems, has built-in safeguards, or at least incredibly demanding entry requirements, that prevent causal paradoxes and limit our ability to freely roam through time. Yet, this does not diminish the wonder. The very act of asking, "Can we bend time with technology?" has propelled humanity to incredible scientific achievements. It has spurred the development of technologies like GPS, which profoundly impact our daily lives, and it continues to drive research into the fundamental nature of time, space, and reality itself. This ongoing quest, this persistent curiosity, reveals the universe to be far more extraordinary than we ever conceived. The science of time is a story of incredible elegance, a delicate balance of forces that governs everything from the hum of a particle accelerator to the precise beat of a satellite's clock. It reminds us that even if we can't build a machine to revisit yesterday, the moments we experience are part of a grander, more flexible cosmic dance. Where are you watching from tonight? And what time is it in your part of the world? Are you under a midnight sky filled with stars? Or is it early morning with the soft sound of birds just beginning to stir? Maybe you're winding down from a busy day or lying in bed, letting your thoughts drift upward like a leaf caught in a breeze. Wherever you are, whatever the hour, thank you for spending this time here with me. If you enjoyed this quiet journey through the science of time, I'd be so grateful if you'd leave a like or even subscribe to The Sleepy Scientist for more gentle explorations like this one. I always love hearing from you, so let me know in the comments where you're listening from and what time it is as you begin to close your eyes. And if you're still awake, gently drifting, I hope the wonder of time, its history, its science, its beauty, has left a soft imprint on your imagination. May your sleep tonight carry you somewhere light and boundless. As always, this video is for entertainment and relaxation only and is not intended to provide any medical advice. Thank you for watching, and until next time, keep looking up.